Thank you for organizers for invitation. So I will start actually from point there. Yesterday, Andreas talked also about Gaussian measure and different inequalities related to the Gaussian measure. So let me start from again the measure itself. So we have density B gamma n. So we have here 1 over 2 pi to n over 2. And e2 negative x squared over 2. So we are working with these measures. So let's go a little bit back in time and see what was the origin of B theorem of inequality. So if you, in case you don't know, so we already saw yesterday multiplicative Minkowski inequality. So let me remind. Sorry, I don't know.
You're not doing this on the intention.
So we have here 1 minus t k0 plus tk1. There you go.
If you break it.
Break it.
Then it will be short, it's small.
Reduce the angle. It's an angle.
ฟิลิปปินส์ยิ้มถอยเอา
So, yeah. Now you will remember that you enjoyed my talk. At least at some point. So, we have a Gaussian measure of k0 to 1 minus t, and here measure of t1 to power t. So we said that actually, if we will take this delay to a little bit more special form, we will get the following. So let's take the following parameters. So here we had Liran Minkowski. Now we are taking t to be 1/2, and instead of different bodies k0 and k1, we will take delays of the same body k. So k0 will be ak, and k1 will be just bk. Then we obtain a Gaussian measure of special delay of body k, a plus b over 2, and this is at least product of ak, bk, and all these squared. So here we can see immediately, even if you don't know anything about Gaussian measure, currently we can recognize the relation to basically arithmetic geometric mean. So if we say, till now we did not say anything about symmetry of k, it's not required to Minkowski. So here we are saying that our k is convex. And now, so we know that this inequality, geometric arithmetic geometric mean. So then, if we actually take in k not be just convex but also symmetric. So here we are working in Rn, and this is our Gaussian measure in Rn space. So then we have that this delay will be actually entirely inside this delay. So that this was actually, since we are working with this measure, was a basis for a question of who asked what about symmetry body? If we will take can not be just convex but also symmetric, can be improved by replacing body A plus B over 2, okay, by this one. So the question was, it was formulated in 2002 and proved 2 years later. By they're asking.
I think it appeared in Lata's SCM notes from 98, or 90 actually, before that, 4.
Work, I don't know. I saw it from 2002. No?
Latala was S theorem, Latala Herscovici.
I was not.
It's a different.
I was not there when they talked between them, so I can just be supported by articles that I found. Maybe my search was not perfect. I don't know. Okay, thank you. So. Fradelisi and Moray. And I apologize if I'm saying names incorrectly. Okay, so they actually proved that if we consider two Gaussian measures, then indeed, sorry, so, and this holds for all positive numbers and B. And now we are just, from this moment, we are talking about convex sets K. So the requirement for convex set presents also here. And actually, so the result actually states that the measure gamma n, if we consider it as a function in variable t, this is log concave in t. These two conditions are actually equivalent. So then, from equivalency of two these conditions, it was also extended to more general case. So then the same delay in all directions was replaced by different delays in different dimensions of R. So let me just mention. So if we are taking AK, this just set of all points of form AX, their X is in K. Now, the extension is that if we will take e to power x times k is defined as pointwise. Will be points of form ax1 by 1 e to power xn by n, and y, this is the point in k. So we can see here different extensions in different dimensions, in respect to different dimensions. And it was proved also that also this norm is also log concave. So this norm was log concave in T on space R. Now we are moving to Rn. And this is the, again, following the equivalency we get here from the theorem. So the theorem that now for any xy from Rn, we get that Gaussian measure of e to xy plus x plus y over 2k will be, again, at least a square root of Gaussian measures of e to power xk, e to power yk. So, and the question that was asked in article was also about symmetry. Is it required or it can be omitted? Is symmetry required? And so we are going to a series of different works that consider different aspects of this inequality. So, for example, work of Liran Rotem, 2013. They consider.
Has nothing to do with the conjecture. No, the conjecture is symmetry, it's very obvious that it's required. But the Rotem, I told you, Rotem had talked about different conjecture.
Okay, thank you.
For the conjecture, you can do it dimensional one.
Works of Orli Herscovici from 2012, and also Saraglu from 2016. In these works, it was considered that actually taking dimension n to be equal to, they got that happens that for all even log concave measures, the B-inequality holds. Then So another work of Liran Rotem, also from 2014, considered uniform measures on convex body. And for uniform measures on convex body, again, the B-inequality works.
In dimension, in what dimension? Dimension 2, I think. Dimension 2.
Dimension, yeah, dimension. Okay. Yeah, thank you.
What do you mean by this statement? The gamma n is replaced by the uniform measure on some convex body?
Yes.
And then you apply it to another one?
Yes.
Yeah, okay.
So the same type of inequality. Then we have work of Liran Rotem. From 18, they consider Gaussian mixtures, and they show that certain Gaussian mixtures for all dimensions n satisfy actually the strong B theorem. And another work related to this, Galyna Livshyts, and Liran Rotem. Pretty recently in 21, they show that strong B theorem holds for all rotation invariant non-concave measures. So in our work, we consider stability of both B theorem and its strong version. So, and we had the following results. So let me. So let's say that B is strictly greater than A. K is origin symmetric and convex. So if we consider the Gaussian measure of this delay, it will be less or equal than square root of products of Gaussian measures. Times 1 plus epsilon. And here epsilon is positive and small enough. Then we have that either the in radius of K is greater or equal than 1 over K square root of log C log B over A squared over n squared epsilon, or in radius of K is less or equal against some constant C square root of n over A. Here we have epsilon to 1 over n plus 1, and log B over A to negative 2 over n plus 1. Maybe write it here and just, so this is our K, and this is R.
Before you erase, so this work by Brodsky, Lubois-Yang, and Zhang and Seroglu is about Minkowski, right, and how it's connected to the B theorem. I was just wondering, so can your stability result then be translated to stability about log Minkowski?
Our result is very Gaussian and cannot even be translated to the B theorem in other settings.
Okay.
Extremely tough one.
Okay, thank you.
Will you say something what this means, these bounds for the in radius?
Okay, so we have here two boundaries. So if we have this stability, so our epsilon is very small enough comparing to the dimensions of our space, so we get actually that the body K should satisfy one of two conditions, either one of two. So oid greater than square root of log, oid less than something else. And this actually, I will write a strong B theorems, stability of strong version, and then I will compare and talk about both boundaries. Okay, so it will be in. So if we consider strong B theorem, then we have formula. So we fix parameters alpha, beta, delta with positive, and then also beta of xy such that length of x is bounded by length of y. Again, our K is origin symmetric, convex. And again, we have this stability. So, again, we are speaking about small enough epsilon. And we are taking here set sigma delta, which is exactly set of dimensions where we have a difference between our vectors is significant than our fixed parameter, greater than our fixed parameter. We take sigma delta alpha of k, all points on boundary of k, such that if we consider sum of coordinates, square of coordinates over both coordinates, it also exceeds our fixed parameter alpha. Then we have there exists point z on the interval xy such that Gaussian perimeter of set omega delta alpha of easy k is bounded by beta times perimeter of the easy k, or, and here we will see again conditions on in radius. E to y minus 1 square root of log delta squared alpha beta over n squared epsilon, or here we have again rk less or equal c e to x to minus 1 square root of n epsilon to 1 over n plus 1 delta squared beta to negative 1 n plus 1. So we can see here that conditions we have, in both cases we have conditions on in radius of our body, body K, or in Stone B theory we have another additional conditions that the stability happens also if the perimeter of our set, the difference happens is different, is bounded. So, but what does it mean? So what are those radiuses? And here, first of all, stability exists, but then the equality happens. When does it happen? When we achieve equality in B theory. So let's see, we are speaking about asymptotical bounds. So because we are speaking about n, and if we are going asymptotically with our in radius, we can see that it's while n is increasing, we get that either our radius is going to be in infinitely large, so we get that our K actually is coincide with whole space Rn. Or on opposite, the inner radius is shrinked, and then we get that set K is actually empty interior. These two cases that equality happens, and again it happens asymptotically. The same conditions are actually similar here. The entrance of n is similar to entrance of n in a regular B theorem. So again, the equality happens either then the whole space, or it has empty interior. And then also there is another case for strong B theorem. There we have some a special representation of body K. There K be some K0 times H xy. Here K0 is belonging to H per. So here our body K has a special representation, and Hxy has the structure that here we include points from Rn such that the coordinates there we have this sigma xy. Should I finish?
No?
No? Okay.
I mean, eventually, yeah. You have had 10 minutes at least. I think, yes.
Okay. So here again the body K has the special structure, and one of our applications. So I'm not going to prove this thing, but
Sorry, don't mean to interrupt, but I think you're speaking. Started, quoted fast. I don't know.
okay.
Go on.
Continue.
Yeah.
Okay.
Just sit here.
Okay. So the application of this result. So this theorem, the strong B theorem, it is proved actually already using the stability of standard B theorem. You continue? Yeah. Okay. So, and here we applied by dimension by dimension for strong B for the stability of strong B theorem. So let me just represent the application of this result. And then we will arrive to consensus about finishing. again, we are taking symmetric convex body K. And then there exists unique maximizer T for supremum of gamma Tk over all T, where T is linear volume preserving. Later on Rn. So the meaning of this theorem that actually it's applied to Babcock maximal Gaussian measure position that let me remind. So Babcock maximal Gaussian measure. Position. So again, for convex symmetric body K, show that a gamma of K is at least as gamma of Tk. Again, we are speaking about operator, linear operator, which represents the volume of bodies. So, and the question here was about, once we have the result, we are asking about uniqueness of these results. And the question was about the operator T. Is it unique or not? And applying our result, we actually showing that there exists a unique maximizer. So it implies that the equation for Babcock's, the answer for Babcock's equation is affirmative, and such maximizer is unique. So we have here uniqueness for operator T. So that's what I would like to tell today. Thank you for your attention.